now, but I want to introduce you to. I first want to go over the feedback you guys gave me, and then I want to introduce you to something called sums of games. And the theorem is one of these theorems where you read the theorem and you're like, oh, I don't think that's that important. So what I'm going to do is back off the sums of games and show you the NIM game solution, the multi-pile NIM game solution. And then we're going to go back to the Sprague-Grundy functions and a theorem. And it seems like this theorem makes things harder, but it doesn't actually. So the implications of that theorem, the intuition of that theorem, why it's important, is really great. And then I'm going to introduce you to the game Go, which is, I think it's a combinatorial game. I haven't really looked at it that carefully, but it's a very, very popular game. And I think that game was actually at the beginning of the movie A Beautiful Mind. I think they're playing it outside. So what's the results of the feedback? Well, somebody asked for, most people were fine. Somebody asked for more group work. So I thought maybe what's happening is some people are isolated and not working in groups when they really want to work in groups. That's okay. I'm not shy, if you couldn't tell, but I do know people who are. So I'll try to make sure that everybody's in a group and gets a chance to work with somebody. And then I was asked for guidance on the final project. That's coming up. So what I'm thinking, I want to give you something very, very solid, at least by this Thursday. But what I'm thinking of doing is having a video of each of you explaining your project in 3 minutes. So that's a little hard to do. You have to practice, and I'll give you a little guide of how to do that. That's where we're going to start. You have to be able to explain something quickly because we're going to have posters and people are going to come in and look at it, right? And we're going to invite people to come here. And the way we're going to do that is we're going to do a video invitation. So I'm going to put all the videos together and then make a compilation of them. Somebody who's an extrovert and who loves to be in front of a camera has to define what is meant by a combinatorial game. Otherwise, you'll get people asking whether something's a game or something's not a game. So we'll start off with that. And then I'd like to send it all the way up to the president of the university and make sure that they're excited enough to come. That's good for you, although if you're balking at saying, I don't want to do that, remember that this is a new age. You're going to have to interview. You're going to have to put yourself out there. And you can be an introvert and do it still successfully. So this is practice, and this is a chance to practice that. Then I'll give you also a guideline for how to do your lit search. I use something called the PRISMA guideline. You can take a note on that if you want to. It's PRISMA. It's very, very specific. You have to actually identify the keywords that are placed in your search, and this is how many found that were relevant to that keyword, and this is how many you discarded because you looked at it and found out actually had nothing to do with your problem, and so forth. So you have this little flow chart where you place through everything that you found. And I'll give you a little seeds to start out with. So you might take a paper, plug it into a search engine, and then get that paper cited this paper. You'll find a whole tree of things in that method. But you have to write that method down of how you found those papers. It's really, really a good idea to read the history of all the different, what's been done before, so you can identify. Some of you are picking projects that nothing's been done before on it. That's great. So wherever you explore, I can give you more well-defined projects, if problems to explore in that problem. Some of you are picking problems that have just been touched recently, but not much, like your project with the triangles. So that's not much has been done there, and so you can easily identify some problems where not much has been done there. So and then comes the conjecture stage and everything. So I'll give you guidelines of what to do and how to get that done. Okay, any questions on that? I actually want to blog about this because I think that going without tests here has been really fruitful for me. I watched everybody else saying, I have to give my students a test. I thought, oh, I don't have to do any of that. Nobody has to be stressed out. And even the end point seems fun. It doesn't seem like I'm torturing people with a test. So I love it. Sums of combinatorial games. So this is a bit bizarre. Imagine yourself playing several games at the same time. So you have, let's say, NIM here. You have your corner game here. You have the triangle game here. So there's a bunch of games. And I'm going to make a new game out of that. I'm going to say, okay, there's 2 players. You first are going to pick a game. So you're going to go, oh, I'm going to play the triangle game. And then you're going to make a move on that game. And then the next person can choose a game. So maybe they choose NIM. And they make a move on that. So they go back and forth like this until there's no moves on any of the games. That's a sum of combinatorial games. If you want to torture someone, this is what you do. Put out several games down and say, we're going to play the sum of all these games. So each player, when their turn comes up, we can select any game and make a move on that particular game. When there's no more moves possible in any of the games for player X loses. Well, I can represent that as graphs. Suppose that all of these combinatorial games, they're going to result in progressively bounded graphs, which we discussed last time, that you're going to have a finite amount of, you're going to have a maximum amount of moves over the whole scope of things. Remember, we had the 10 coins out, and there was 11 total possible moves for that directed graph maximum that bounded everything. The least upper bound, or the soup. So we can take those n games and put them together into, we can take each game consists of the vertices and the edges. So we can take the vertices and the edges, and that should be an en, and put them all together. And these graphs can be put together in a new graph, where V is all these V1s through Vn's, and they're ordered pairs, and we denote that as a sum, G1 plus G2 plus, it doesn't really make sense because you really sum up integers or sum up numbers. So this is just notation. And how do we do this? We do this in the following manner. V is going to be a Cartesian product. That means that you represent them as an ordered pair. You did something like that when you were doing the Grundy function for each vertex. You're putting the losing winning position as the x coordinate and the Grundy function value as the y coordinate. So we can do that whenever we have groups of objects that are related to each other. So the vertices, to be an element in this set, means that x1's a position in game 1, x2's a position in game 2, and so forth. So there's an n tuple of positions that come from the vertices that are specific to each game. It may be really wildly different games. You might have Nim as your first game. Dots and boxes is not a combinatorial game, but you can imagine dots and boxes could be a game that you put here. So x2 could come from dots and boxes. x3 could come from Go, which is a game I'm going to show you today. So you have all these different positions, and then you group them as a ordered pair or ordered group and tuple. So for each x, which is an n tuple, it's not a vector because we don't have a vector space, but it's an n tuple, define a set of followers. You can talk about the followers for that n tuple by this funky way, and you're thinking, why are they using this crazy notation? So I'm taking and mapping the n tuple to another n tuple, and I keep the followers of x1, and then I have all the other coordinates stay the same. So all the other positions stay the same, and I union that with, remember, the followers are a set. You remember when you had the node and you looked at the set of followers and then you mexed it? Okay, so it's a set. So these guys are sets. So you can actually union sets. And then you do the same thing with F2, but hold all the other positions the same, and so forth. And then you do it then again with Fn, the last one. So these are all the followers. So it's like an n tuple of followers, kind of, but it's a set. So for example, that F2 would represent all the vertices that follow x2. So you look down your directed graph. Good to go? This is starting to look pretty easy now, right? That's the idea. So that's a set of vertices. Recall your one directed graph. You just had one. Yeah, I've got n of them. So one directed graph, and that one directed graph gave you other nodes, right? That's what the followers were. So those followers form a set of vertices. And so all of this is back in the big n tuple of vertices. So it's a subset. So when you move in that n tuple, what does a move mean? Well, a move in the vertex, the n tuple vertex, what it means is it consists of moving one of the guys in here to a follower in that game. So remember, you have to select the game first, and then you move. The graph game with the n tuple stuff is called the sum of the graph games G1 through Gn. So recall multi-pile nim, right? You can really think of this 3-pile game, because there's 3 different piles, as being the sum of 3 1-pile games. Remember I asked you what's the relationship with this and single pile nim? So each one of them, if you just worked with one of them, what would the subtraction set be for if I would just had this pile alone and I didn't have the other piles? 1, 2, 3. So this is really the subtraction set 1, 2, 3 with 3 elements in it, right? So each one of them is single pile nim. And then when I take the graph and put it together, and you drew the directed graph of single pile nim. You know that's pretty easy actually. And the Grundy function is pretty easy to calculate. So this is actually the sum of these 3 single pile nim games. So I want to go to this multi-pile nim because I need to define something called a nim sum. It's not dim sum, so if you're hungry, that's not what it is. It's nim sums. So if you just start playing with this, and some of you kind of were doing this as at your desk, I graded your stuff so you can see it, but what would you do if it was your turn and there was only 1 pile? Teresa? Yeah. There's only 1 pile in multi-pile nim, and it was your turn.
I would take the whole thing.
That's right. Take the whole pile. Did you cheat? So take the whole pile and you win. So we know what to do in backward induction if we were to that case, right?
Yeah. I was just being greedy.
What if there were 2 piles?
He said 1, then he takes 1, but then he wins because he's last.
So I kind of have to
Take half of it?
make sure that they equal numbered. Because if you make sure, some of you are saying this, I think it has to do with the number of things in the pile if there's an even number of things. But I think you can get it also if there's an odd number of things as long as they're the same number of things. So somewhere in some of your analysis, you were coming to that point of it has something to do with parity. Because if you have the same number of things in each pile, you really have an even number of tokens left. If I take that and I make them equal size, then the next player should do this. Because if they take everything, then you're back to 1 pile, and then you won. So that will mean that you do this, and you win. So that's the little strategy if you have 2. Now it gets harder if you have 3 piles. They can't come up. It's hard to do backward induction like that. With single pile, and then we already did that in class. It was actually pretty easy and a little bit fun to come up with what the winning strategy would be if you have the subtraction set and you go backward in time. But you can't do this when you have multi-pile nim easily. So this is something we call the nim sum. I'm not going to prove the things here. I think I'm doing a proof today. But the nim sum of 2 non-negative integers is their addition without carrying in base 2. That's what the nim sum is. So in formula form, if you haven't seen this, I had a professor once. I had him in my junior year of college at a research experience, and I didn't know this. And he said, I learned that when I was in 2nd grade. Well, we do learn this when we're in 2nd grade. We learn base 10 addition. But you could do the same thing. That's what we use is base 10 arithmetic. But you could expand any number into any base. So you could do this in base 2. And then you're living in the matrix, right? Because these coefficients are only going to be 0s and 1s. So we call this the binary representation of a number. So for example, 18, the way you figure this out is you look at 18 and say, what's the largest power of 2 that goes into 18? No, the largest power of 2. We're going to expand base 2. It's going to be 4, right? Because 16 is the closest number that we can get. That's a power of 2 to 18. And so I know that this is important. This is important because I do a proof today. So this tells you that you're going to have 1 times 2 to the 4th. If I add 8, which is the next power of 2, to that 2 to the 4th, I've jumped over my 18. So I don't want any 8s in there. I don't even want a 4 in there because 16 plus 4 is 20, so that's going to jump over the 18. I just want a 2. And that gives me the 0 at the end. So the binary expansion of 18 is 1, 0, 0, 1, 0. So I show my kids this before they're in 2nd grade. So what's a nim sum? Well, I can take two numbers. Let's say one of them is a to the m, 2 to the m, so forth. And I have a y. Well, the y might be smaller, it might have less coefficients, right? I can just take a smaller, let the smaller one be the second one, okay? Well, I'll just front end a bunch of zeros. So if it's a smaller number, I'll put a bunch of zero coefficients in front so that they both are power 2 to the m. What do I mean by nim summing these two? We use this representation, which I felt like I helped somebody with their praxis once. I kept seeing things like this up there. It's not a nim sum, some funky thing they're doing on the praxis, but they're adding these two x and y's. What it means, they just add the coefficients, but mod 2. So if you get a 1 plus 1, what are you going to get? 0. So for example, it's really interesting. We just talked about examples here. So when I was looking at nim sums, there were no examples. I just made one. So making your own example is a really great way to learn material. And it takes time. So I told you the hardest part of things like real analysis is figuring out how much time you have to spend. That's because you have to front end all these examples and you didn't realize you have to. One day you realize you have to, and then you find it pleasurable, and so you don't even know 2 hours has gone by. It happens. Look at rate my professors. Every time I teach a proofwriting class, they say, I really like doing this. Probably don't say that in pre-calc, but in the proofwriting classes they say, because they understand something that was challenging, and they understand what kind of time was spent in it, and they get it. So make your own examples. So 22 is 1 times 2 to the 4th plus 0 times 2 cubed and so forth. And 51 is 1 times 2 to the 5th plus all that stuff below, done the same way I did the 18. If I want to nim sum these two, I take the 22 and I front end it with a 0 because this is a power 4 and this is a power 5. And I line them all up and I add straight down. So wherever there was a 1 plus 1, it becomes a 0. That's it. And then you replace it back into binary notation, crank that thing out, and you get 37. So the nim sum of 22 plus 50 and 51 is 37. Make sense?
How did you convert it to zeros and ones again?
Which one?
Like 2 to the 4th becomes 0.
Okay, so 22. What's the largest power of 2 that is right before 22, that doesn't overstep 22?
2 to the 4th.
Right, because 2 to the 5th is 32, it's jumped over. So that's why I know that the leading coefficient would be 1 times 2 to the 4th. Right? Then I look at 8, which is the next one down. Well, if I take 8 and add 16, what do I get? Jumped over again, right? So it's too much. So I don't want any 8. So I give it a 0.
She used that first 0 because there's not 2 to the 5th.
Right. I front end this with a 0. Is that what you wanted to know? Okay.
And the numbers are right above it, so obviously that's why it's like.
Got it?
Yeah.
Right.
I forgot about the 2 to the 5th.
But so I did this on purpose so that, first of all, when I'm sitting at home, I'm tired and confused. So I aligned everything up. I wish I was as careful in the rest of my life as I was in mathematics. I'm sure the rest of my department feels the same way. No matter how messy someone's office is, when they do mathematics, it's always neat and nice. So try it out now. 62 and 47. Nim sum that sucker. Show all your work so I can see what you're doing.